This is video number 14 for Computer Science 1124. And if you think, wow, that's a different setup, you're right. I turned the whiteboard around. It's supposed to be rainy most of the day today, so I didn't think I could depend on natural light, so I hope my track lights in my kitchen will make the board bright enough that you can see it. We need to be bright because we're going to talk about algorithm analysis. G-O-R-I-T-H-M. The sequence of instructions to solve a problem. Analysis. You may be thinking to yourself, well, we've already analyzed bubble sort. We've turned that every which way but loose and said all this stuff about it and designed all the steps. Well, that's not officially the analysis of the algorithm. That was a description. That's algorithm description. Whoa, Trout! Trout, no! Sorry about that. For it to be algorithm analysis, we're going to have to answer this question. How good is bubble sort? Abbreviated. Which is a different question from how does bubble sort work? Now that we should be thoroughly familiar with how bubble sort works, now we can look back at it and say, thinking deep thoughts, I think it's going to be this good. But that's a pretty open, generic question. So I'm going to answer it with another question. How good is bubble sort? Answer, question. Compared to what? Well, we don't really have a lot to compare it to, do we? We've looked at that algorithm for putting a list in order, but not much more. But you know what? We're in luck. We don't have to look at any other algorithms because the answer is how good is bubble sort compared to what? Compared to itself. Strangely enough. We compare bubble sort to itself. Now, that sounds kind of silly, I know, but that's because here's what we're going to do. We're going to answer this bigger question, or try to. How badly does bubble sort's behavior degrade or get worse as the list, which is the list that it's sorting. It's the centerpiece of the bubble sort. We've got to put this list in order. How badly does bubble sort's behavior degrade as the list gets larger and larger? And we'll come up with a fairly precise measurement of that. We'll be able to predict just how bad bubble sort is going to be if we have a list that's, say, twice as long, or maybe a list that's 10 times as long, or maybe a list that's 1,000 times as long. We'll be able to make, surprisingly, a pretty close prediction of how long it's going to take bubble sort to run, or in our case, how many comparisons bubble sort's going to have to do on a list like that. I'm going to start with just some observations. We'll just look at a few examples, and I'll try to get a juicier marker. And we'll see if we can get an intuitive feel for this. Observation. In the best case, and I put dots because I'm not necessarily going to finish that sentence right now and be done with it. In the best, well, first of all, what is the best case? You might think, well, duh, of course, the best case for a sorting algorithm is if the list is already in order. That is true for bubble sort. It's not true in general. Bizarrely, perhaps, one of the fastest known sorting algorithms to man, the quicksort algorithm, actually has its worst case behavior if the list is already in order. Whoa, that's beyond the scope of this video. In the best case, and I'll put parenthetically here, the list is already in order. I'm going to have to slip in an aside here. I've already thought of something that we need to discuss before we go any further. Aside. Aside, an observation inside the aside. Aside. We need something to count. We need something to count so that we can predict, well, since we're counting this, we know it's going to take twice as many of those things to get the list in order this time. Or it's going to take 10 times as many of those things, whatever those things are. And I guess there are several candidates, We could count the instructions. How many Python statements are going to have to be executed as we run the bubble sort algorithm? Turns out that's not a particularly good choice. There are too many. Past a certain point, it's just kind of white noise. We're counting a lot of instructions that are not really an integral, serious part of putting this list in order. But wait, the first and erroneous version of your Lab 10 code. Instead of counting constructions, we can count swaps. Why not count how many swaps have to be done? And that will give us some measure of how good the bubble sort algorithm is behaving, how well it's doing its job. The problem with that, though, is that gets an X as well. Too few. The opposite problem. For example, let's say we're going to put a list that's already in order, put it in order. Doesn't make any sense, does it? But if the list is already in order, then what does bubble sort do? If you review in your mind back with me how that operates, it'll go through and compare everything, and it'll never change the flag. So it will realize the first time through the list, you know what, this list is in order, I don't have to do this anymore. And it falls out of the while loop. Having performed 0 swaps. Now that list that you were visualizing along with me that was like 5 elements long. Oh no, it was really 5 million elements long. Well, let's visualize it again then. We go through bubble sort, it goes through all 5 million elements, comparing each one to the next one. And it doesn't do any swaps because that list is already in order, according to our hypothetical example situation here. So once again, no swaps occurred. And if we're trying to compare how well or how poorly bubble sort behaves compared to itself, it's going to look like the behavior is identical for a list of length 5 and a list of length 5 million. And common sense tells you, you know what, that's not going to be true. It's going to be executing a lot more instructions. It's going to take a lot longer to run if the list is 5 million elements than it is if it's only 5 elements. That's why I'm going to suggest, a strong suggestion, that swaps are too few of those. They're not enough to give us a good feel for how the algorithm is behaving. You know where we're going with this, right? Instructions, that's just a flurry. There's too much going on. I can't count all that anyway. And it'd be a big mess. Swaps, I only do that under special circumstances, so there might not be any swaps at all. There are not enough of those. It turns out, for the bubble sort algorithm and for a lot of sorting algorithms, if not most of them, a good thing to count is comparisons. Ding, ding, ding. Not too cold, not too hot. Comparisons turns out pretty much just right. We compare elements even if we don't swap them. And we are going to have to do more comparisons as the size of the list gets bigger. And we're certainly going to have to do more comparisons if we have to go through the list several times because it wasn't in order the first time. But comparisons is going to be our winner here. We are going to count comparisons and let that determine for us whether or not the algorithm is behaving good, bad, if it's behaving as we predicted. I meant goodly, badly, make those adverbs. So let's count comparisons instead of swaps or introductions. Now I'm back to black. That was the end of the aside. In the best case, the list is already in order. Here's the list. 1, 2, 3. No, that's too close to index numbers. 7, 12, 13. There. Those are not index numbers. Here comes bubble sort. I need to put this list in order. And we know how that operates, right? It compares the first pair. 7 and 12. You know what? 7 and 12, you're in order. I think I'll leave you alone. But I did compare. I did have to do a comparison. Count. I counted you. 1 comparison. Shifting right along. What about 12 and 13? Well, 12 and 13 are in order. I don't have to swap those. Check. But I did do an additional comparison. That might have been 20 instructions I just now executed, or maybe 25. Whoa, that's too many of those. I'm not going to count those. I didn't do any swaps at all. So it looks like the algorithm takes 0 time to execute, and that's misleading. It's going to take more than 0 time, even if it's just checking to see if they're in order. So what we've got here in the best case, we're done, and we only had to do 2 comparisons. I'll abbreviate. Comps. 2 comps. That was example 1. Here's example 2. Let's do a longer list. I used 5 elements before. I'll use 5 elements again. No, I'll stretch it up to 7. We'll make it really big this time. -9, 0, 3, 5. You'd think it'd be easy to make up a list of numbers. I'm really struggling here. -9, 0, 3, 5, 8, 12, 1, 2, 3, 4, 5, 6, 175. There we go. Put that list in order, bubble sort. I'll call the function. I'll pass it that list. And it says, you know what, that first pair's in order. I think I'll leave that alone. -9 is less than 0. 0, 3 in order, check. 3, 5 in order, check. 5, 8 in order. Rapidly we see a pattern developing here. But it's still got to do the comparisons. And then the while loop will realize, you know what, that flag didn't get set, so I don't think I'm going to have to go through this again. But it's still going to take longer than execute than this. Not a whole lot longer. It's still a pretty short list. But it has to do more comparisons. 1, 2, 3, 4, 5. 5 comparisons. Now, I'm going to parameterize this a little bit, like we did going from the first graphics project 3 video to the second. See if I can generalize this. 2 comparisons, what does that have with how many things are in the list? Well, the last thing on the list doesn't have a pair of its own. It's not the first of any element. So there's actually 1 fewer pairs to compare than there are elements in the list in this case. So in comparisons here, that's equal to n minus 1, where n is the size of the list. I'll even label it. N elements there. Well, n is not 3 down here. N is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. You know what? I left out something somewhere. 1, 2, 3, 4, 5, 6, 7. Let me do those comparisons again. We ask that you bear with us. That's in order 1. That's in order 2. 3, 4, 5, 6. How about 6 comparisons? What alerted me to the fact that 5 was probably wrong? Because there are 1, 2, 3, 4, 5, 6, 7 elements, and the pattern is going to hold. This is n minus 1, where n, the number of things in the list, the length of the list, in this case, was 7. N is 7, the number of comparisons we did was n minus 1. N equals 3, the number of comparisons we did was n minus 1. Now that I've fixed it, good thing I fixed it, now I need board space. Any questions? In the best case, whoops, hope I didn't knock it out of focus. In the best case, bubble sort does n minus 1 comparisons on a list of n elements. And since this is analysis, and analysis is kind of mathy, I use a mathy word. Thus, we say, we, you, I, the American people, all the computer scientists of the world, we say bubble sort is big script O. Order n in the best case. Order n. I'll put a dash instead of a period. The increase in the number of comparisons and since we're using that as sort of an indicator indirectly of how many instructions are going to have to be executed for bubble sort to operate, we can also expect that it's also going to describe the increase in the runtime, the increase in the number of comparisons, and the increase in the runtime the time it takes to run your program in milliseconds or whatever we're using as our measurement, the increase in runtime is directly proportional proportional to n. I'm trying to tell us something. Let's see if we can untangle that and turn it into something closer to plain English. What is that trying to say? Well, it's trying to say, let's say n. All my black markers are going dry at the same time. Let's say n is 5. Here, this is an abstract representation of a list of length 5. And the runtime. Here's an abstract representation of the runtime in a different color. Maybe, whatever the time unit is, microseconds, milliseconds, whatever, maybe it takes 3 time units. Order n says, if we increase n, let's say we double it. I'm going to double n. Dot, dot, dot. If n is 10. Since we've made this observation, now this one, there wouldn't be any way to guess 3. I just made up 3. I could have said 13. I could have said 35. I could have said 300. Forget about that. But I observed it. I ran my bubble sort algorithm on a list of length 5, and it spit back that it took 3 time units. If that takes 3 time units, then when n equals 10, twice as long, guess what? I can make a prediction. I'm going to do a purple prediction. I'm going to purpley predict. It's going to take 6 time units. Seems easy enough. That's what it means by directly proportional. Even though it's still the best case, we're still talking about the best case. This list of length 5 was already in order. That list of length 10 was already in order. But if I observe that this list of length 5 took me 3 time units, then I'll predict that a list of length 10 is probably going to take me about 6 time units. I could actually get the number of comparisons exactly, couldn't I? I could say that, well, if n is 5, and my corrected math on the previous whiteboard, then it's going to take 4 comparisons. That's going to take 9 comparisons. Let's do all of them. Let's put those two lists together. Whoa. Where n is now 15. I've got a list of length 15. Oh no, how many time units is that going to take? Well, the parallel line down here, where I'm measuring runtime up next to the size of the list, I'm going to predict it's going to take 9 time units. How did I get that? Well, the increase from n equals 5 to n equals 15 was a factor of 3. So my prediction about runtime, the best runtime, is going to be 3 times the runtime. 3 times 3 is 9. See how that works? We could even make a table. That was a fig. This is a fig. Now that I write fig, I'm going to erase all that and make a table. Shows where I was getting the numbers I was using to label my parallel bars there. Here, the black mark. I'm going to switch to purple. I'm sorry, but I don't think I got blacks at work. Here's table n and the runtime. Just put them right next to each other. We could also, you know what? We could throw in comparisons just for good measure, because those are easy to calculate. Let's say n is 100. Let's quit messing around. A list of length 100. And I run that. Oh no, how long is that going to take? I have no clue. I have to get me a benchmark. I have to make an observation. I have to run it with list size 100 and see how long it takes. I think it's going to take about 7 time units. How did I calculate 7? I didn't. I ran it on my computer and I timed it with my little microsecond timer. And it said, sorting the list of 100 took 7 time units. I'm even going to circle this because this one's special. Comparisons, you know what? You're irrelevant now to this table. I'm going to get you out of here. 7 time units. I'm going to call this one observed. I observed that a list of 100 took 7 time units. Why would I even be interested in that? Well, I might want to know how long is it going to take to do a list of length 200? Or maybe, you know what, a list of length 500. Or a list of length 1,000. Or maybe yet a list of length 10,000, 100,000, whatever. Having this as my benchmark, this base point here, I can make predictions for all of these. How long is it going to take Bubble Sort to sort lists of this size if the list is already in order? And away we go. Well, if I double the size of the list, I'm going to predict it's going to take 14 time units. There's no reason to put a dot there. 200, 14 time units. What about 500? I don't know. Well, it went up by a factor of 5. 7 to 5, if I remember correctly, is 35 time units. See how to play this game? 1,000. Well, I'll go back to the 100. That is 10 times bigger. Directly proportional, 10 times bigger for 7 will be 70 time units. I could have gotten that saying, okay, I'll just jump start off with 500 here. I double the 500, well, double the 35. Either way, I'm going to go back and use 100 each time, I think. Down here, the big one, the grand finale, 10,000. 10,000, no, I'm going to cheat. It's 10 times 1,000. That's an easier math problem. 10 times 1,000, well, then it's going to increase by, I'm going to predict, a factor of 10 on the runtime. This will take 700 time units. Now, I labeled that one as observed. There's no way to calculate that. You have to try it out and see. These are all predictions. I did calculate these. Knowing that it was an order in algorithm in the best case, I'm making these predictions about what the runtime will be. See how handy that could be. I don't even have to run it with gigantic data sets to have a ballpark idea of how long it's going to take to run in the best case. I can predict those. These are all predicted. And it's spelled correctly. Predicted. That's what algorithm analysis is for, or at least part of it. We don't have to run all these cases to have a pretty good idea, a pretty good estimate of how much time it's going to take Bubble Sort to do this in the best case. And notice I keep qualifying that over and over again. How many times have I said best case in this video? Bunch of times. Well, using that whole discussion, order in and the runtimes and all that stuff, that's going to be my benchmark for tackling the more important case, which is aren't the more important things always more difficult? The more important case is going to be the worst case. What does Bubble Sort do in the worst case? And that shall be our next video. I'll see you online.